to check to make sure that we have enough space for the whole lecture, because it would not be good if I think I was recording and it doesn't have enough space to store everything that I want to record. This is our last lecture. Okay, so you guys are happy about that? Good. So we're going to go over the final exam, which is, this one is the actual final exam from last year, but because I covered the material differently compared to last time, so it's not going to be exactly the same questions, okay? So I just want to give you guys an idea of what kind of question I'll be asking. And as I work on the, this past exam, I'll kind of give you some idea of how I might modify the exam. All right.
I noticed that when I went through it, it's a lot of like newer material or like stuff that you did the past second exam. Is that going to be the theme of? Is it comprehensive or?
It is comprehensive, but I won't ask questions that I have not taught. So the minimum spanning tree, not going to be there. A-star algorithm, not going to be there.
Okay, but like, do you have like any sort of like percentages that you're going to emphasize previous material to new material? Like,
I don't have any percentages.
or just like kind of like what you would say, like is it going to be mostly new material with a little bit?
It's mostly newer material. So proportionally speaking, there'll be less material from earlier in the semester and more material, especially stuff after the second exam. So graphs is going to be definitely going to be the majority of the questions.
Yeah.
But it's not going to be it's not going to be just about graphs. So there will still be questions about functions, relations, set theory, and stuff like that. Okay. There will be one problem of resolution. So we still have to remember how to do CNF and resolution and stuff like that. Okay. All right. So what we'll do today is, I'm just going to go to that document that I sent you guys earlier today. Some people might have a chance to get to it. I'm not sure how many people got a chance to at least take a look at that one. I'm going to apps first just to make sure that I'm signed in, so because otherwise I won't be able to open the link. And here is the link. I do not have the correct font set installed on this computer, or at least in the live distribution. So that's why the text is going to look a little different from what you guys see. All right. So just ask questions whenever you have any questions, and we'll go from there. All right. So the basic rules would not be changed compared to last semester. The time obviously is changed. We even have the same room. It's still going to be open book and open notes and no electronics. I don't really see any chances where you need a calculator. If you do want to use a scientific calculator, that's okay. You can bring one with you. I don't think you will have to use it. But if that, just as a backup, you can bring one. Once again, the assessment is an individual assessment, so it is important that we all just work on our own questions. So that part is pretty much the same as the second exam. Use additional sheets of paper if you need any additional sheets of paper. Just one point about this one, if you use any additional sheets, make sure that you write your name on those as well, okay? Because I have had cases where I have a loose piece of paper and I don't know whose loose piece of paper it is. So you might want to write your name on it, just so that I can tell, oh, okay, this belongs to that person, and staple it together when I have a chance. Write legibly, same thing as before. Make your answers as complete as possible, which means, if there is a way to explain something, go ahead and explain it. Okay? All questions have equal weight. I'm not really sure about this final exam, so I will make it clear in the questions. Okay. The final exam will still account for 40% of your final grade, and people need 37.5 to pass this class with a C. Just as a reminder. And I can see some people saying, oh, so that means I don't even have to go to the final exam. All right, so the first question is on the A-star algorithm, which is not going to be asked, okay? I cannot ask you anything about the A-star algorithm because I haven't really talked about the A-star algorithm. Yep?
Can you start recording?
I believe so. Let's double check. No, it's here. Yep, it is being recorded, and the audio is recorded as well. So it's good. It's good to double check. Okay. So what I would also do is I'm also going to give you a listing of the Dijkstra's algorithm. Okay, just in case you forget what is the Dijkstra's algorithm, and even those open book and open notes, you forget to bring the algorithm with you. I'm going to have it in the test. Okay, so I will have Dijkstra's algorithm in the test. It may or may not be the Wikipedia one. In other words, I might change the algorithm just slightly so that how things are represented may not be exactly the same, but it will still be the same algorithm. So the question that I will be asking is not going to be based on the A-star algorithm, which is actually a little bit more complex, as you can see, because if you remember from the previous class where we traced the Dijkstra's algorithm, it's not quite as bad as this one. Okay, so this one is kind of worse in a way. There'll be questions like this where I have to change the question. Consider the graph to the right. Vertex A is the origin vertex. Vertex D is the goal. So I want to go from vertex A to vertex D. The heuristics function does not apply because when we are dealing with Dijkstra's algorithm, there's no such thing as heuristic. So I want you to trace, in this case, the Dijkstra's algorithm and clearly indicate all the update operations. So everything that has a left arrow, so anything that has an update needs to be reflected. You have to tell me how things are updated. But it will only be applied to the Dijkstra algorithm. Okay, so do you guys want to do this one? Just kind of briefly? Okay. How many people still remember Dijkstra's algorithm? Or should I bring it up? You guys still, for the most part, remember? So let's see if it is okay not to bring up the listing, okay? Because I want to kind of do it by hand first, and then we can go back and take a look at the algorithm. Okay. All right. So I need to set up my document camera, and I found the same company that makes this $100 document camera also makes a $160 digital whiteboard, which no doubt is based on the V-mode idea, which is basically just tracking a source of infrared. It's $160, and you can mount it basically anywhere within the classroom. I know $160 sounds like a lot of money because it's about the same price as an algebra textbook.
You wish.
No?
No.
It's cheaper?
It's so much worse.
Really?
Yeah.
How much is an algebra textbook?
Over 200.
Over 200?
Yeah.
Oh wow! Because I was talking to a math professor this morning, just this morning, and he said, "Oh, an algebra textbook is now $150."
His is.
Do
That's
you
nice.
not have access to the website?
Yeah, that probably doesn't include the access code.
That's it.
There's
Okay.
another $80-90 right there.
Yeah.
And they give you a package deal, right? They save you like
Oh, yeah,
what,
sure.
$30, as a result of that. Yep.
It's a deal.
Not really. But
Oh,
if you
wow,
find
I-
a textbook on Amazon for $20,
On the
that's not
website,
it.
Oh wow! I did not realize.
Semester you use it.
Wow.
Yep. If you're
Well, Pearson is big in terms of having the digital content. And what I also heard from the same math professor is the software would crash often, and he suspects that it's crashing because it's being over restrictive, because it doesn't want copyrighted content to be distributed.
It's a good monopoly.
It's a racket.
It is a racket. It's math. It's not. There's nothing proprietary about math. And math has not changed on an annual basis either. When you're talking about USB, SATA, memory bus and stuff like that, yeah, we make progress once in a while. Okay, we are now on what, USB 3.0, right? Okay, so computer textbooks you can kind of expect it to change once in a while, but math, I mean, algebra is algebra. And by the way, the professor that I talked to is he's Ben Edgen, I think E-D-G-E-N. So he's really big on open source, and I was helping him to set up his Ubuntu system because he didn't feel comfortable upgrading from 15.4 all the way to 16.4. So I had to tell him, okay, just upgrade to 15.10 first, and then from 15.10 you can upgrade to 16.4. So I was in his office, and talking about stuff the whole time.
Tech support on the side.
Hmm?
Tech support on the side.
Yeah, tech support was the actual reason why I was in his office, but we talked about other things, like how we're all going to be using Canvas and not Moodle, not D2L. It's going to be Canvas in not too long, actually. The whole state is going to use Canvas. Yep. All right. So we got the document viewer up and running, and we just have to go through the algorithm to trace it. All right, so there we go. Okay, so A is the starting point, so our set Q, okay, remember in the original algorithm, we have a set that has all the vertices. So in this case, we have A. I wonder if there's a way that I can place my camera where my hand doesn't cover what I'm writing. I guess not so easily. A, B, C, D, E. Okay, so Q, which is the set of vertices that we need to consider, will start with every single one of the vertices in the entire graph. Okay, and then what we need to do is to do the initialization. There are two things or two attributes that we have to remember or we have to associate with each vertex. One has to do with the current known shortest distance to that vertex, and then the second one is who is the previous. Okay? So I'm going to use a slightly different way to look at this. Okay, so I'm going to use A, B, C, D, E as a table. So these are the vertices. And then what we'll do is to have these two columns to keep track of previous and also the cost to get there at this point. It's not cost in the algorithm, they call it, what was the term that they used?
Value?
Value? Distance, yep, D-I-S-T. Thank you. All right. So initially, the initialization is to initialize everything so that they have no previous and the destination is going to be infinite. And I understand in Iraj's class it is slightly different, it's represented slightly differently, but in this class, this is how we're going to keep track of all of this stuff here. So previous is not applicable for every single one of the vertices. So I just use NA here to begin with. And you can see how I leave a lot of space because I'm going to cross out and update as we go through the algorithm. Distance is initialized to infinite for every single one of them. Now, this is where you can kind of optimize the execution of the algorithm, because the very next thing we do is we say, okay, whoever is starting is going to have a distance of 0 because we are already there. And that turns out to be vertex A in this particular question. So we just cross out this infinite and put a 0 here. Okay. Are there any questions about the algorithm or the execution of the algorithm? Yep.
Is this going to be the same way you want us to map it? Like for an exam?
Yeah.
Would this method be acceptable?
Yep. Because this way I can see, you can update the properties or attributes. Okay. So the next thing we do is we want to pick a particular node to begin with, and there's a particular name in the algorithm. I'm just going to say, V. Okay. So V is the vertex that we are examining. In this case, we have to pick the one that has the least distance to it known at this point. And because A is the one that has a 0, so we're going to pick that one. So that's the reason why we are picking vertex A. But as a result of picking vertex A to expand, the set is now going to have one fewer element. A is no longer in the set. And this is how we can remember which vertex have we expanded at any particular time. Q is the set to keep track of that. When Q becomes empty, then we have expanded every single possible vertex, then we can exit. Because now, if there is a shortest path to something, we would have found it. All right, so now that A is the vertex of interest, we want to find all the neighbors of A, and update those neighbors if applicable. Okay, so now we want to look at the neighbors, and in this case I'm going to look at neighbors as a set. So A has two neighbors. A neighbor is basically a vertex that is directly connected to, in this case, vertex A by an edge. And edges in this case are directed. So that means vertex D and vertex B are the neighbors. So we look at vertex B and vertex D, and because this is a set, how you write this down is not important. You can write D, comma B, B, comma D, they're all the same. And which one you consider first also does not really matter because they're independent. Okay, so now that we have these two neighbors, then we say, okay, for each neighbor of V, which is vertex A, we want to calculate if I go through A to that neighbor, how much is that going to cost? Is that going to be a lower cost? If so, we have to update the previous node or the previous vertex as well as the distance. So I just randomly pick B to consider first. And so if I go through A to go to B, since the cost to go to A is 0, and the edge going from A to B is 3, so that means the new distance to go to B is 3. The current known shortest distance is infinite, which is a huge value. So the new way obviously is a shorter way. So that means at that time we have to update this infinity so it becomes 3. And we also have to update previous to A. So this particular action combined is saying that I just discovered a new way to go to vertex B through A, and it has a lower cost than the best path known up to this point. That's why we're updating the table. Is that okay? All right. So even though the mechanical stuff is kind of important, that you understand how to follow the algorithm, it is also equally important to understand what we are doing and why we are doing it. Okay, so B is done. We now look at D, same thing. So we say, okay, how much is it going to cost us to go to vertex D through A? Now the cost to go to A, or the distance to go to A, is 0. The edge going from A to D is 2, so that means this new way only has a cost of 2, which is less than infinity. So once again, we update D and say that the new way to go there only has a distance of 2, but we have to get through A, go through A to get to vertex D. Are we doing okay so far with this code? Okay. So then we go through, then we are back to the outer loop in the original algorithm, which is saying, okay, as long as the set Q is non-empty, we still have to go. And the set Q is non-empty, we still have B, C, D, E as vertices in that set. And once again, we pick the one that has the lowest cost in the set as my next vertex to expand. Now, I'm not going to reconsider A because A is no longer in the set Q. So of the elements in the set Q, B, C, D, E, the one that has the lowest or the shortest distance is vertex D. So D is the one that I pick. So now I say V equals D because that's the vertex that I choose to expand, and Q is now has one fewer element. It only has B, C, and E because D is now deleted from the set, or we subtracted from the set. So now that B is the focus, we want to look at, now that D is the focus, we want to look at the neighbors of D and say, okay, let's look at those particular vertices. So the neighbors of D is, we have vertex C and vertex B as the neighbors of D. And we go through the same logic. We look at, let's say we look at C first. So we look at C and we say, okay, if we go through D to go to C, how much or what is the distance to get to C using this particular route? The route going to D is 2. Excuse me, go ahead.
What was the mechanic for us eliminating A as a element to the set? Like, I understand why, but how did we do it?
How do we represent it?
How do we exclude A from the set end?
From
The set end.
From
Or
set
A.
N?
Like, because it's adjacent to it, so.
But the edge is not going into A.
Okay.
So that's why in this case we do not consider. Now, on the other hand, if the graph has an edge going from D to A, then A would still be a neighbor that we have to consider.
So if it was like a double arrow, then we would still have to consider it.
Correct. Or you have an extra edge here going from D to A. Because this is a directed graph, so that means, you know, if you see an edge, you have to ask the question, which vertex is the origin and which vertex is the destination. Yep. Mhm.
But in our first step, we made the vertex from V equals to A.
Right.
And we took it out of the set Q.
Yeah.
But if it has an arrow going back to A, is it still in set Q?
No. Every time you expand a vertex, you have to take it out of the set. Now, A can still be a neighbor of another vertex, so it still have to be considered as a neighbor going through that little logic. Now, obviously, in this case, because A already has a distance of 0, it's not going to be updated. But if it is a neighbor, you still have to consider it. But it's not in Q anymore. We are not going to re-expand A and look at A's own neighbors. But we'll consider A when it is a neighbor of somebody else. Okay. All right. So let's take a look at C. You know, C is, if we go through D to go to C, okay, on the graph here, okay, and I need to switch my pointing equipment because, you know, this cannot be used to point in here. So if we go through D to go to C, the cost to go to D is already known to be 2, which is what this number is. And from there to C, we have an extra edge that has a cost of 4. So to go through D to go to C, we have a distance of 6. The current known shortest distance to go to to go to C is infinite. So that means we have a better way to go there. So we update the infinite to 6, the infinity to 6, and then the NA is now reflecting D because we are going from D to C, and the distance is 6. So now that C is done, we go back to B. Now this is a prime example of you can revisit the same vertex multiple times because it can be the neighbor of many other vertices. So just because it's reconsidered doesn't mean it will be updated. We just have to consider. So in this case, we are considering going through D to B. Now going to D, we have a distance of 2, and going from D to B, we have a cost of 1. That edge has a cost of 1. So we have, once again, a distance of 3. So this time, it's up to you to decide whether you want to update it or not, because it doesn't really make a difference. Okay, whether you want to go to B from A directly, or you want to go to B through D, has exactly the same cost. So typically, for algorithms, we use a greedy algorithm, which means we don't want to update unless it is necessary. Yep, go ahead.
That's what I was going to ask. There's still a cost for the machine if you have to do an update.
Right. So typically, we don't do the update because it's not useful. So that was another hand. Yep.
Yeah. So even though we're updating, or we don't have to update B again because its value is 3, but now we have a different previous.
Potentially, but since going from A to B has a cost of 3, and going from A to D and then to B also has a cost of 3, we're not going to update it because that update is not going to buy us anything. So we'll leave B exactly the way it is because the new path has exactly the same cost. It's not going to make any difference. Going back to the trace, now we have considered all the neighbors of D. So we look at the set of Q, which now only has B, C, and E left, and then we pick the one that has the lowest or the shortest distance. B has a distance of 3, C has a distance of 6, E has a distance of infinity. So out of these 3, B is the one that I will pick next. So I will pick B to be expanded. Q is now only has C and E as elements. So now we have to look at the neighbors. And we have to look at the neighbors of B in this case. B only has one neighbor. It only has a neighbor of C. So we are going to reconsider vertex C, but this time we're going through B. The cost to go to B, or the distance to go to B, is known to be 3. The edge going from B to C has a cost of 3. 3 plus 3 is 6. So once again, we have another way to go to C, but it has exactly the same distance as the known path, which means there's nothing to update. We just leave it the way it is. Is that okay? Are there any questions about why we're not updating anything in the table? Okay, it's all good? Yep, go ahead.
In the question, originally you said to show updates. How is scratching it out showing the update?
Yep.
Like that's enough for the test, just to scratch out the previous number and put a new number?
Yeah, because I think in the test I can design the numbers so that if you do it in the wrong order, it's not going to work out. Besides, you still have the sequence of updating Q, V, and N. Q, V, N, Q, V, N, Q, V, N. So I can still see which one you're expanding and what neighbors you're considering, so I can still see whether you're following the algorithm correctly or not. Is that okay? Because otherwise the alternative is to update all of those individually too, which is really kind of hard for me to see as a final result. All right, so we're done with done with B as the vertex to expand, and now we can move on, and we pick another thing out of Q. So out of Q, we only have vertex C and vertex E left. Vertex C has a cost of 6, and that's the one we're going to pick because vertex E has a distance of infinity. So now we say out of those two, we pick C to expand, and then Q. Okay, I'm just going to wrap around here. So Q is now only having one element left, which is E, and now we have to consider the neighbors of vertex C. The neighbors of vertex C only has one single thing, it only has one neighbor, which is E. So this time we have the set of neighbors being exactly the same thing as Q itself. There's nothing wrong with that, it's just kind of coincidental, but there's nothing wrong with that either. So now we have to consider this neighbor, which is vertex E, and we're going through C to E. The distance to go to C is 6, and then the edge going from C to E is 2. 6 plus 2 is 8. 8 is less than infinity, so we have to update the table. Okay, and this is going through C. That's how we update the table. Question? No? Okay. And now we are done with that iteration. We go back to the beginning, and this time we pick we pick E, vertex E to be variable V, and Q becomes empty because we have just removed the last element out of the set, and it has no neighbor, which means there's nothing else to do. And then we go back and we check whether Q is non-empty or not. Q is now empty, and the algorithm will exit. So that's the end of this entire trace. So we do okay so far? Okay? Yep.
Was it Dijkstra algorithm or it's just manual way to do that?
This is the manual way of tracking Dijkstra's algorithm. Yep.
Are there any other ways to have the same cost of A from A to B?
From A to
Oh, wait, do we need to write down the way that we came up with, like ACE or ABCE? Once we find out that the way one will be more expensive, longer, or shorter.
I don't understand the question.
Do we have to present our results in the A, B, C?
No, this is the entire result. Your result is this table. This is the actual
path itself,
table.
the actual.
But there's
cheapest
not
path.
just one single path, because Dijkstra's algorithm doesn't find the shortest path from one node or from one vertex to another vertex. It finds the shortest path from a set of origins to all the destinations, all the other vertices. In other words, you can, okay, let me just give you an example of what I mean by that. So the generalization of Dijkstra's algorithm, let me give you an example where we have two starting points. So A, B are starting points. This is C, this is D, and then we have E, F. Just to make it kind of fun, we can go from F back to C. Okay, so if you look at this particular graph here, I can designate 2 as starting points. I can designate vertex A, which is this one here, as one of the starting points. I can designate this one also as starting points. But when you read the original Dijkstra's algorithm, there seems to be no provision of having 2 starting points. But if you think about the algorithm itself, to have 2 starting points is very easy, to do. What do we do when we only have 1 starting point? What differentiates the starting point from all of the other vertices? It started off with a distance of 0. Exactly. So in this case, we can have vertex A and vertex B to start with a distance of 0. So now they are both considered starting points. Is that okay? So when the Dijkstra's algorithm is done, it will actually tell you how, what is the shortest distance to go to every single vertex. So there are certain vertices, like vertex E here, that is only reachable from vertex A. Vertex B cannot get to vertex E. But Dijkstra's algorithm will figure that out and say, oh, by the way, the cost to go to vertex E is the cost of the edge going from A to E, because there's only one edge here. There's not a path, it's just one single edge. Yep.
What if we're given starting at A, destination F?
Okay.
There's no way to get to there.
Then it will continue to have a distance of infinity. Yep. The algorithm will complete because every iteration of Dijkstra's algorithm, you are obligated to pick one element out of the set. When you have multiple elements in the set, then you prioritize based on the distance, right? But when you have multiple elements, they all have the same value of infinity, just pick any one of them. Then you have a cost of infinity. Now, when you have a cost of infinity, and you say, oh, I can go from here to here, but if it is not reachable, what is infinity plus 2? Infinity. So it will still work. The algorithm, quote unquote, will still work. It will still finish, even though it doesn't seem to make any sense. Okay, the new cost is infinity plus 2. Well, that means it's still infinity. You have not really changed anything. Yep.
If we had 2 starting points, would they have the same sets? Or
Would they have the same?
Would B have E in its set? Or no?
Okay, well, let's go ahead and work on this one, okay? So we'll work on this one, and we'll assign some weights here. This one does not really matter. There's only one way to get here, so we'll just call this 5. There are 2 ways to get to D. Let's make this fun. So one is shorter, so 3 and 4. 2 ways to get to C. But I want to make C kind of interesting because I want to go through F to go to C. So this is actually the shorter path, but this one looks more expensive first. I guess that's not there. Yeah, we can probably, we can make this 7. Yep, that would work. And then we'll make this one a 9. There we go. Okay, so this is my new, new question. So let's see how. So this time I'm going to shortcut the whole thing. I'm not going to keep track of the Q, or I use a different way to keep track of that. So I still use a table, which is A, B, C, D, E, F. We have 6 vertices. Let me just count. Yep, we do have 6. And then we have the same 2 columns. We have distance, and then we have previous. And I'm just going to use a check mark next to the vertex to say that it is not in set Q anymore, that it is already considered. All right, so initially we want to initialize distance and previous the same way, which is infinite, infinite, infinity, 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 and these are all NAs. Okay. So they're all NAs here. All right. Then the next thing we want to do is to initialize the starting points. Now we have 2 starting points because we have A as a starting point and B as a starting point. Now, which one is a starting point is completely up to the question to decide. There's no particular reason why we pick A or B or both to be the starting points. It's just that I want to see whether you understand how to track this or not. So since A and B are both starting points, the distances will now update both will be zeros, and the previous will still be not applicable because they are starting points. Are we doing okay so far with how to initialize? Yep.
Why don't we put like the starting point for the previous node of A is A?
Because that implies you are going from A to A, because in some graphs you can have edges going from the cell or going from a vertex going back to itself. Okay, all right. So in this case, this is the starting point, or this is how we start up the entire thing. And because you are supposed to pick one thing out of set Q, now everything is in set Q, all the vertices are in set Q. You're supposed to pick one that has the lowest distance. We got two that has a distance of 0. Just randomly pick one, okay? You can start with A, you can start with B, it doesn't really matter which one. So which one do you guys want to start with?
B.
A.
Do you guys want to vote?
Just pick one. Just do it.
A.
Let's do it. Yeah, let's try A, because I think A is the interesting one. If we start with A, there will be more updates. Okay, so let's pick A, and this is how I denote that we are looking at A, and A is now out of the set Q. Okay, because I just don't want to use the other way. There's not enough room to do it. All right. So now that we have picked A to expand, we have to look at all the neighbors of A. A has got 3 neighbors. It has got C as a neighbor, D as a neighbor, and E as a neighbor. So in this case, just to help myself mentally track which neighbor we need to consider, I'll do it in a alphabetical order. So in this case, we'll start with C. The first round is pretty easy because the current known distance to C is infinite, which means anything is better than that. So 9 is a better one than that, and then we say, okay, let's go through A to C. Huh?
Previous should be A, not 9.
Oh, sorry. Fortunately, 9 and A are pretty close. I said as long as I can read it, it will still count, right? Okay. Okay. But thank you for pointing that out. Okay, so we are done with C. The next one is D. Same thing. So D is we have a new distance of 3 by going through A. And the last one is E. E is pretty much done because that's the only time we actually get to E. So the new cost is 5 going through A. Okay, we're done with this iteration. Now we can look at all the remaining vertices in the set Q, which is everything except for A. Okay, so out of all of those, we have to pick the one that has the lowest or the shortest distance. B has the shortest distance of 0, so we're going to pick B. So we look at B, okay, we put a check mark next to B and say, okay, we are now currently exploring B. And looking at B, we go like, okay, who are the neighbors of B? B has got 3 neighbors. It has got C as a neighbor, D as a neighbor, and F as a neighbor. And once again, we'll go through the alphabetical order. So we'll first examine C as a neighbor of B. We now have a distance of 7. Because the distance to B itself is 0, the edge going from B to C has a cost of 7. 0 plus 7 is 7. So that means, we found a better way to get there. Okay, update the current known shortest distance from 9 to 7, and say that, okay, we are now going through B to get to C. Are we doing okay so far with that? And then we look at the next neighbor, which is D. The current known shortest path to D, or the shortest distance is 3 going through A, but if I go from B to D, it has a cost of 4, which is no better, so nothing to update in this case. And the last one to consider is F. The current known distance to F is infinity, and the new way going through B to go to F is 5. Obviously a better way to do that. Okay, so we update the distance to 5 and say, okay, let's go through B to get to F. So now we are done with another iteration of Dijkstra's algorithm. The next iteration, only has 4 elements left in Q, being C, D, E, and F. Out of those 4, D has the shortest distance, so D is going to be the next one that we are going to expand. Okay, so we'll put the check mark here, and we look at D. Yep.
So D points to A?
D does not point to A. The arrow goes in this direction.
Oh, okay.
Yeah, sorry about the back.
We skip C because C has no neighbors. C can't go anywhere.
We skip C.
C has a value
Too
set.
costly.
Yeah, but you put a check next to A, you put a check next to B, but you're not even going to look at C because.
Because when you
There's
pick
nowhere to
something
go.
out of Q, you have to pick the one that has the shortest distance.
Oh, okay.
So of all the remaining vertices in Q, we have to pick the one that has the shortest distance, and C does not have the shortest distance. It has the longest, actually. Yep, question?
Where do you get the list of the neighbors of each node?
By looking at the vertices, by the edges, yeah. So it's graphically represented here.
So you in the actual language in the programming language, you
Okay.
have to keep track of them somehow, or what?
Well, in this class, which is different from 430, okay, so the way we track things is just by two tuples, right? So in this case, if I want to tell you what is V, which is the set of all the vertices, that's just A, B, C, D, E, F. That's the set of all the vertices. But if I want to give you the set of all the edges, okay, so E, so because this is a directed graph, it's a digraph, so that means I have to give you 2 tuples. So I have an edge going from A to C, that's one element. I have another one from A to E, another one from A to D. I have another one from B to C, B to D, B to F, and the last one is from F to C. So that's the actual quote-unquote representation in this class, because
So
we
you
are.
just cross them and find out which one is. See, besides graphically looking at the graphics and looking at it,
Uh-huh.
how would the or programming way of doing this? Just kind of.
Well, in this class, we just say find a neighbor, and based on the edges that are presented to you. So in this class, we don't really use it doesn't boil down to actual programming action. It's really just kind of abstract, high-level action of given the graph, given the representation, either using the set notation or using the graphical representation, go find me all the neighbors of a particular vertex. So we are not as concerned as cisp440, where you say, okay, let's use a heap, let's use this or that type of representation. In this class, we just say, okay, it's an abstract operation.
Okay, thank you.
I think that's what you meant.
Yes,
What you
that's
asked.
exactly.
Okay. Yep. Okay. So we are looking at D. D is an easy one because D has got no neighbors. So we just say, okay, we're done with D. Okay, so now that we have 3 elements left in Q, being C, E, and F, let's pick one that has the lowest or shortest distance. E and F have both the shortest distance. If they have the same, just randomly pick one. Okay, you can pick E, you can pick F, doesn't really matter. So I'll just go ahead and pick E. Okay, so we look at E, we expand E, or try to. In this case, E has no neighbors, so there's nothing to do. So we're down to 2 vertices left in Q, being C and F. F is the one that has the shortest distance. Let's go ahead and expand that one. F has 1 neighbor. It only has 1 neighbor because we only want to count outgoing edges from F, not incoming edges. So if you just look at the outgoing edges from F, C is the only neighbor. Okay, so we have to look at, okay, what happens when we go from F to C? Oh, okay, it seems to be a lower cost distance, because the known shortest distance to go to F, according to the table, is 6. The 5 is 5, and then the edge going from F to C only has a cost of 1. 5 plus 1 is 6, but the known shortest distance to C is a 7, so we have to update it. So we have to update this 7 to be a 6, and then we have to say, oh, don't go from B to C directly, let's go through F. So we have to update the previous and also the distance. Is that okay? So this example is kind of interesting because you can see how vertex C is updated 3 times because of the way I set up the cost of the edges. Okay, so now that we are done with C, we are done with all of this particular iteration, and the set only has C left, and then we say, okay, let's go ahead and expand C. C has no outgoing edges, so we are all done. So the end result is this table here. This table is the actual end result of the algorithm. It doesn't tell you just the shortest path to go to a particular vertex. It tells you the shortest path to go to any vertex in the graph. Yep.
In the final, how do you want us to write the result? Like, should the table will be fine with the checkbox?
Right. So the table reflects, the actual outcome, but you have to show the steps. Like, this is the original queue. This is the vertex I'm expanding. These are its neighbors, and then the new queue becomes this because we are removing that vertex out of it. And this is the next one, the next vertex that I'm expanding. These are its neighbors. So you kind of have to go back to the example that I showed earlier. This one I didn't want to go through all the steps because I just wanted to be relatively quick. Yep.
What if the path to the destination is shorter than the path to another node? Like, say.
But there's no destination. Remember, there's no such thing as destination. We are trying to figure out the shortest path to every vertex. So would that change the nature of your question? Yeah. Okay. Yep.
So this is kind of more of like a mechanics.
Okay. Okay.
So there's a way of us picking out which element of Q equals B, which one we're picking out. That's like a minimum, right? We select the minimum value. Is there any mechanic for selecting an N, where you just choose any arbitrary element from the set N? Like, do you pick them in any specific order, or is it just random?
It is not random. When you pick which vertex to expand out of Q, you're picking the one that has the shortest distance to it at this point.
But for N,
for the neighbors?
Yeah.
Oh no, there's no particular order.
Okay.
So you can visit the neighbors any way you want to. There was another hand. Did you have a question? Okay. All right. Yep.
So why is A 0? It's just a started with A?
Because A and B are both considered starting points.
Sorry.
And all the starting points have zeros to begin with because we are already there. Yep.
For the final, do you want us? Can we just do like this, or do we have to include the queue? And
You have to include the queues because I have to see the sequencing of how you expand things. Because this doesn't really tell me as much. Okay, it's a good way to summarize, the actual outcome, but I want you to show me the sequences as well. Okay. So the big question is, why do we start with 2 vertices in this case? Why? It doesn't make any sense, right? Because anytime you want to start to look for a path, there's only one starting point. Well, as it turns out, this is the backward way of looking at things. Okay, look, think of it this way. Okay, so think of A, B, C, D, E, F like this. Here's A, and here's B, and then you have the other ones. These 2 can represent the location where you have a charge station, and you are a Roomba robot. Okay, the vacuum cleaner thing. These 2 are the charge stations. So the charge stations are actually quote-unquote the destinations. That's where you want to be. Okay? Then what about the other vertices? They represent the rest of the room. Okay, or the important junctions of the room. So now you have A is already done, B is already done, so you have C, D, E, and F representing other places in the room. So what you're really doing is you're trying to calculate, if I'm at this spot in the room, how much time or what is the cost to go back to one of the 2 charge stations. It doesn't matter which one you get back to, as long as you can get back to one of the charge stations, you can recharge. So that's basically why, in some cases we want to consider multiple starting points. But it's actually the other way of looking at things. The so-called starting points of the algorithm sometimes represent the actual destinations that you want to get to. Yep.
In that case, how are A and B connected? Do you just
They're not connected.
Do you
They're
just magically spam, in whatever place you want to start at, and then you just proceed from
They're
there?
representing two locations where where you have two charge stations in a room.
No, but I'm just saying, theoretically, if you're using A and you're done with that side, how would you go to the other side if it's not connected? See?
That's not really the idea, though.
But that's not what we're trying to do. We're trying to find, you're at a certain place in a room, you want to find out, okay, how do I get to a charge station as quickly as possible? So, okay, so in that particular interpretation, so if you are in, okay, let me remove the pen because it's covering one of the vertices. So if you're in E, you have no choice but to go to the charge station A. You don't have a choice. But if you're at spot C or spot D, then you can choose which charge station you want to go back to, because you can go back to charge station A, or you can go back to charge station B, and based on Dijkstra's algorithm, you can pick the one that is closer to you. Does that make any sense?
Yeah.
Okay. And the more interesting part is when you're at D, at C, how do you get back to the closest charge station? You don't actually go from C directly to B. You go through F, and then you get back to B. That is the shortest path. If you are at vertex C, then you go to F, then you go to B, which is your charge station. Now remember, the way we see it here is not necessarily representing the distance or the difficulty from the perspective of a robot. Yep.
You brought up the robot example, but I just wonder whether Google uses it for maps to find the location.
I do not know the exact algorithm that they use to find the shortest path. It probably is based on, but not exactly the same thing as A*, because this is not, it doesn't make use of heuristics. In other words, this one is quote unquote blind in a way, okay? It would just kind of pick out the next one or the one that has the shortest known distance and pick that one. It is also known as breadth first search, okay? Because it's going for breadth, just instead of depth. A* is more informed because it makes use of heuristics, and as a result, in many cases, A* will give you a better solution given a fixed amount of time.
Okay, thank you.
Yep.
Can you go over number 2?
Number 2, okay, moving on to question number 2. Using vertex A of graph Q1 as root, draw 3 alternative spanning trees and blah, blah, blah. I'm not going to ask spanning tree problems because we haven't really talked about spanning trees. Yeah, so that won't be asked because we haven't talked about spanning trees. Although I can talk about spanning trees in 2 minutes and.
Or we can go on to question 3.
Let's say that for the lab.
Okay. I will talk about spanning trees in 2 minutes, but I won't ask questions. How about that?
That's
Okay.
very
So it is still an important concept. I think you guys should know about it.
No,
So,
I want for test review though. But test review.
I understand, but it is still an important concept. 2 minutes. Okay, so a spanning tree is basically a tree that can visit every single vertex. Okay, so from A, if I want to draw a tree, D, oops, this is D and this is D. Okay, it is still a tree. Now, if I have an edge here, it's no longer a tree. So I want to go to C. Now, since I did not say minimum spanning tree, I can go from B to C, and then C to E. That is a tree. That's one spanning tree. The alternative spanning tree is not to go from B to C, but instead go from D to C, and remove this one. That's another spanning tree. The last one is to get rid of this one, and get rid of this one, and do it like this. That's another spanning tree.
Okay.
So less than 3 minutes.
That was better.
Spanning trees, but remember, I'm not going to ask questions about spanning trees because we haven't spent enough time. Yep.
So spanning tree is a tree?
It's a tree that spans and touch every single vertex.
Oh, okay.
Yep.
With only one edge in between.
And a tree means you cannot have multiple edges. You can have any number of outgoing edges out of a vertex, but you can only have up to one incoming edge, and you have to have a root that has no incoming edges. All right. So question number 3 is, instead of using the conventional G equals to VE representation, a graph can be represented as G equals to Vn. Here, n, do not confuse this as a variable n in the A* algorithm, is a function so that nv returns a set of neighbor vertices of V. In the case of a directed graph, nv is a set of vertices that are heads of edges where V is the tail. Okay. In the general case, describe the function n by filling in the blank spaces in the following notation. In other words, n is a function. What is my domain and what is my codomain? And in the specific case of this particular graph in question number 1, define n as a set. Your answer should be in the form of n equals to, in curly braces, the elements inside the set. Okay, so this is really just asking how do we represent a graph as an alternative. Okay, as an alternative to the VE, we can define a function that maps vertices to its neighbors. We have pretty much done that as we go through the algorithm. So what I want to do is just quickly go back to the graph here and superimpose, well, not superimpose, but to display on the side how we are going to use the function n to take care of this problem. Okay. Here we go. All right. So we know that n is a function. So the first answer is what is the domain and what is the codomain. Okay. The domain is what do you think? It maps what to what? It maps the vertices, right? So which set represents the vertices? V, okay? Uppercase V is the set of all the vertices. Q is a set only used in the algorithm itself, only used in Dijkstra's algorithm. So that's why we don't use Q. And what are we mapping it to? The neighbors, and the neighbors is a set of vertices, right? So, not quite, okay? Because each neighbor, which is a vertex, is mapped to a set of vertices. Okay, so that means the codomain is not a set of vertices, it is a set of vertices. And there's a way to do this, okay? We talked about this kind of special thing that we can do with sets, and what is it called? It's called a power set. Very good. Good job. All right, somebody actually studied. So it's the power set of V, where it is all the possible subsets of V. It is a set of all possible subsets of V. Now, obviously, this function is most likely to be, okay, let's think about the 3 properties of a function. Is it going to be injective? Is it going to be surjective? Is it going to be bijective? Okay, so let's look at those things. What makes a function injective?
One X goes to one.
It's every different element has to map to something different in the codomain. That makes it injective. Okay. So in this case, is it going to be injective? Looking at this particular graph, is it going to be injective?
No.
It is not injective, which automatically means it's not going to be bijective. Is it surjective? Now, surjective. What is the meaning of surjective? Just a quick review.
All the elements of codomain are used.
All the elements of the codomain are used. Very good. So if you just count the number of elements in the domain versus the number of elements in the codomain, what do you think is going to happen? It's not going to be surjective, because in this case, because it's a power set, it means the cardinality of the codomain in this case is 2 to the power of the cardinality of the domain itself. In this case, because the domain has 5 elements, it means the codomain, which is the power set of V, is going to have 2 to the power of 5, which is 32 elements. Now, if your domain only has 5, and the codomain has 32, it cannot be surjective. So that means it is not injective, it is not surjective, and certainly not bijective. Okay? All right, so this is just a little reminder or quick review of the concepts. So if I want to spell out what it is, okay, so I can now define, using an equal sign, define n as a set. Each element of n, because it is a function, has to be a 2 tuple. The first item has to come from the domain, the second item has to come from the codomain. So in this case, I would start with A and say, okay, who are my neighbors? I got B and D as my neighbors. So it's a 2 tuple, the first item belongs to the domain, the second item belongs to the codomain. Yep.
Never mind, I answered my own question.
Well, if you want to share, that's fine too. It might help the rest of the class.
Well, my question was going to be, what about, how can it be a function if it would, A would map to both BD and DB, but order isn't important to decide?
Correct. So that's why, you can list the DB or BD because it doesn't really matter what the order is. So if you look from the B perspective of vertex B, who are my neighbors? Well, it's only C, but you cannot do this. This would be wrong because it has to be a set with the element of C. Then we move on to C and say, okay, who's my neighbor? E is the only one. And then we look at it from the perspective of D, who are my neighbors? C is the only one. And then we look at E's perspective and say, okay, who is my neighbor? Nobody. So it's an empty set. An empty set is still an element in the codomain because the power set of anything includes the set itself and also the empty set as elements. Yep.
But isn't it true that the neighbor of each one of those, like say the first element A and then the set BD, there is inherently an empty set that is tied to A. So we do have A, comma, empty set.
But the neighbors are the vertices that A can get to, not the neighbors or not the vertices that can get to A. Yep.
Why doesn't D have B and C in its?
D is supposed to have, oh, you're right, D is supposed to have 2 neighbors. Thank you. So D is supposed to have B and C. That's correct. Thank you. All right. So is that okay? All right. So this is going to be one thing that you can expect out of the final exam is it's going to be a combination of the concepts that we have learned. Okay. So in this particular question, I'm combining graph theory with set theory with functions. Okay. But they're all kind of applicable because it's just different ways of looking at things. That's question number 2. Question number 3. No, that's question number 3 already. And I asked, it is not injective, it is not surjective, and certainly not bijective. Number 4 is resolution by refutation. Okay, so this is going back to the stuff that we talked about earlier. And this one, is to draw a diagram representing all possible well-formed formulae in CNF starting with the following. So that means, in using resolution, okay, so each step of resolution is an outgoing edge. Each vertex is a well-formed formula. So I want to represent, what you can do with this one as a graph. Okay, so let me show you the answer to this one.
Can you say that again? Each line is an edge. What was it?
Each vertex is a well-formed formula, and each edge is a resolution. Okay, so let me see how we can position this so we can see both the question itself, which is I only need. Oh, you guys cannot see that. There we go. And that's good. So I can see both now. Okay, so what this is asking is we have W or X, W or not Y, not X or Y or not Z, and then not W or Z, okay? Okay, so this is one vertex, and if you look at resolution, each unique resolution or each resolution with a unique result is one edge going out of this one. So let's see how we can do some resolution here. Not Y and Y can resolve, so I can pick out the Y of the two in the middle, okay? So that becomes an edge, and I can now say, now in the question, because this part here is going to be common to everything, you can just give it a name and refer to it. So if I say this whole thing is A, then you can say A, this is going to be A, but in addition, we have W or not X or not Z. That's going to be the new term by resolving this not Y with this Y here. Yep.
There's supposed to be a wedge between A and the other new resolution segment. Or sorry, not resolution.
Yeah, I'm not using the wedge because I'm using the multiplication to imply conjunction. So in the test, you can do that as well, just to make it easier, quicker to represent your answer. Yep.
Would you have to underline the ones like that, or just?
No, I'm just underlining so that I can keep track of which one has been used. Okay, so I have used the Y, not Y, and the Y to do the resolution, and the other one I can do, there are two more outgoing edges. I can use this not W with this W, okay? So that becomes A, which is this entire thing, but I have a new term which is not Y, not Y or Z, not Y or Z. Okay, I'm not sure whether you can see this or not. Okay. Not Y or Z. There we go. And I have one more way to do resolution by combining this W over here with this not W over here. So the end result is going to be A, and the new term is going to be picking this X here, and then picking up this Z over here. Are we doing okay so far with what I'm asking? Yep.
Why do you name everything A?
Because I don't want to rewrite this entire thing.
Part of A.
It is A
Like parts of
and that.
Right.
Yeah, because every time you do a resolution, you're adding one additional term in your CNF. So I'm just trying to save myself some time, because in the exam you don't want to spend all the time writing all this stuff. Okay. So the next question is, do we have any other type of resolution? So when you look at this one here, we got the not Y, and then we got the Y here. So you can resolve again. And so that will lead to a not Y or Z, and combining this Y with this not Y, so we have not X or not Z or Z, okay? And that is, what do we know about that one? No, it's not false. It's always true. Okay, one of the terms is always true. So this one, this term becomes just true. And because that term becomes just true, that means we're not adding anything. So this is not a new vertex. Yep.
But if we wrote that as a vertex, would that be?
That would still be fine.
Okay.
Yeah. It's just that it doesn't. From the perspective of logic, it doesn't really add anything because we were there already. So that's basically what the question is asking. So when you look at this new term here and you say, okay, can we have any additional resolution because we now have X or Z? And the answer is yes, we can resolve it with this one here. So we have A, X or Z, and then we have this Z resolving with this not Z. So then we have the same situation, which ends up with X or not X or Y, which also means this new vertex is not necessary because it doesn't add anything. But if you are to add it, it becomes X or not X or Y. But once again, we don't need it because it is just the same thing as what we had before. So we look at this one here and say, can we end up with any additional new resolution? And let's see, we have this x that can resolve with this x here. And that certainly would end up with something new. So we have this x resolving with this x. So now it becomes a, w, or not x, or not z. And then the new term is w, or, and then this additional w we don't have to say, we just have to include a not z over here. So that's what the question is asking, is basically every time you do a resolution, we represent that resolution using an edge. And we want to see, what we can do with this graph. Is that okay? So it's basically the same thing that we have done before, okay? It's just, this is a new way to look at things that we have done in the past in the form of a graph. Okay, so I'm going to move on because we are running out of time. Question number 5, modify and redraw the graph of Q1, maintain the order of the graph. So you have to remember what order means in the sense of graph theory. You're free to change the size of it, and once again, you have to remember what the size is. New edges do not need to have costs. In other words, don't come up with random costs because that's just going to take you extra time. Do this modification so that you can demonstrate the following. For each item that I'm asking here, clearly indicate the answer based on the modified graph. I want you to show me a walk that is not a path. I want you to show me a walk that is not a trail. And I also want you to show me a tour. So this is basically a question about the definitions. You just have to go through the definitions, find out what is a walk. The walk is easy, okay? It's just basically vertices connected by edges. But when you look at a path, okay, what is a path? What makes a path a path? So that way you can tell what is not a path. I think it's a repetition of vertex. So you're looking for something that has a repetition of a vertex. And a trail is one that does not have a repetition of an edge, so you have to create a path that has a repetition of an edge. A tour is one that has
origin, it's the start is the same as
it's basically a loop. Yep, exactly. So that's what this question is asking. Question number 6, referring to the graph of Q1, you can see how I'm kind of frugal in terms of not having to come up with anything new, so a lot of them just refer back to Q1. Draw its complement. Once again, it's just a matter of definition. Okay, what is the complement of a graph? So you have to look it up. Basically, it is saying it's a complement based on edges. Okay, so in other words, point out all the missing edges and make a new graph out of it. That's the complement. Yep.
Do we have self-loops in the complement?
Say again?
We have self-loops in the complement?
No. So typically self-loops are not included in complements. Okay. Note that this is a digraph and the complement is going to be a digraph as well.
Digraph meaning?
Directed. So all the edges have arrows. And then the supplemental question is, what is the size of the original graph? What is the size of the complement? There should be a relationship of some kind, okay? So you have to figure out what is the relationship. What is the sum of the size of the original graph and its complement? They should add up to a particular number. What do you think that number should be? No, it's not 1. What is the number of edges for a completely connected graph? In other words, every vertex is connected to every other vertex.
2 times b.
Well, okay, let's do a quick one on this one. Okay, this paper is all used up. I'm going to use a new one.
The cardinality of each.
Yeah, just the number of edges. Okay, so what we'll do is we'll start with 3. Okay, so here's 1, 2, 3. Okay, and I'll look at this as a non-directed graph because a directed graph is just doubling that number of edges. So we got 1, 2, 3. We are all done. If we have 4, then we're looking at 1, 2, 3, 4, 5, 6, and you're looking at 5, and we want everything to be connected, to each other except for itself. So what is the formula? Do we have a formula to come up with this number? Sorry?
Because you have like n-1 connection to the first item, and then n-2 for the second one. It's like
And then we're adding.
Yeah.
Okay? So what is the actual number? But the last one has no choice. The first one has got 2 edges because it doesn't count itself. So when you have n vertices, then given n vertices, the number of edges is going to be n minus 1. We start with n minus 1 plus blah, 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 all the way down to 0. So now you have to find a closed form of something like this. And that's going to be, there's a closed form to that. N times n minus 1, and then the whole thing divided by 2. Okay? So n times n minus 1, the whole thing divided by 2, and n is the cardinality of v. Let's see whether it works or not. When it's 3, do we have 3 times 2 divided by 1? Divided by 2? Yep. When it's 4, do we have 4 times 3 times 2, and then the whole thing divided by 2? Oh, it's not times, sorry. It's 4 times 3 and then the whole thing divided by 2. It works. Okay. So this, well, it's not an exact proof, but that's a demonstration that this relationship works. So for those of you who are kind of not exactly, I wouldn't say curious, but just kind of say, oh, but we have seen something like this before. So the question now is, can you prove that with a set of vertices of n, the number of edges of a fully connected graph is n times n minus 1, and then the whole thing divided by 2. But you have to prove it in the graph sense. Yep. Mm-hmm.
So that formula is not for digraphs, it's just for...
Yeah, for digraph, you just get rid of divided by 2, because every edge is now replaced by 2 edges, one going to and then one coming from.
So double.
Yep, it's just doubling. Okay, so quickly going through all of the other ones. Draw a minimum graph that is not planar. In other words, if one edge is removed, the graph becomes planar. We talked about that a little bit. And then question number 8. Just remember, you cannot have a non-planar graph when you only have up to 4 vertices. When you have 5 vertices, that's when you start to have graphs that are non-planar. Remember that part? Okay. So that means the solution is already discussed. You just have to remember what did we do with 5 vertices. Question number 8. Prove that the A-star algorithm will terminate. Okay. So instead of A-star, replace it with Dijkstra's algorithm. Now, since you already know one possibility of the exam question, it means it's not going to happen. But nonetheless, it will still be helpful to kind of go through that exercise just to show that the loop is not going to be infinite. Question number 9: an undirected graph with n vertices can have. Oops, okay, I provided the answer to one of the earlier questions, but only to people who pay attention. This is going to be useful. But I want to prove this by induction. So the main point of this question is to prove it by induction. So what you need to do is to say, okay, now we have a graph with n vertices. If I add one more vertex to the whole thing, how many new edges am I adding to make this a fully connected graph? That's how you need to think about it. Okay. Question number 10. The A-star algorithm works only if a graph satisfies certain requirements, and so on and so forth. This one I cannot ask because there's no heuristic in Dijkstra's algorithm, so it does not apply. And let's see, that's it. 10 questions. Yep.
Are we going to use graphs that heavily on the test?
Yep.
Okay. Second question: when you're like explaining a path or something, is it just an n tuple where you mention every vertex that you're gonna hit?
A path, you can represent it as a sequence of edges. You can also just make it a sequence of vertices, but then you have to make sure there is an edge between all the vertices.
So you don't care if it's a set or if it's just like you go A, comma B, comma C, or like A to B.
It cannot be a set, it has to be a tuple. It has to be a sequence.
Okay, can you show me an example of how to write that?